Okay, so one of the advantages we made mention of was that producing AC is cheaper than producing DC. So AC is cheaper in terms of production than DC. Last time we discussed how DC is produced. DC is as a result of chemical reaction between chemicals, or when electrolytes, whether in a liquid form or in a paste form, react with electrodes, we have DC. Okay, so imagine producing a bigger battery. The amount of chemicals you will need, then the electrodes to put together to produce DC is huge. Meanwhile, or if it comes to the secondary cells, getting acid, getting the electrodes, fabricating it, it's very, very, okay, troublesome, or to take a lot of time. Meanwhile, to produce AC, all that you require is a field magnet. You need a magnet. Then you need a coil, which is a conductor. You try to let this rotate within, when it is placed within the magnetic field, you try to let this rotate. So some engineers, people even create this. They create their own alternating current to power lights, fans, and so production of AC is cheaper than producing DC. Please, is that okay? Hello, is that okay? Do I have people in the house? Are you there?
Yes, please.
Give me feedback. So that is one advantage. Two, transportation of or transmission of AC, okay, over long distances is easy. Transmission of AC over long distances is feasible and incurs minimum losses and incurs minimum losses. That is why we have Akosombo all okay at the location, but the power generated can be transmitted all the way from Akosombo to Accra, Cape Coast, and so on and so forth. You can't easily do that when it is DC. For DC, you incur much costs. So transmission of AC over long distances is feasible and incurs minimum losses and costs. Meaning you can easily transport alternating current from the production sites to wherever it is needed. If you do that for DC, it will cost a lot of money to do that. Then 3, here I've put 2 points in one. Can easily be transported. and would incur minimum loss. And then the cost factor. So this is 2-in-1. The third advantage AC has over DC is that AC is adjustable. Voltage adjustment, meaning if it is high, if the voltage is high, we can make it lower. So voltage adjustability implies that we can either AC can either be stepped up, or down. So we can either step it up. When we are stepping alternating current up, it means we are increasing it. Or we can step it down. If we are stepping it down, it means we are decreasing it. And the explanation to this is that Akosombo, when they produce current, alternating voltage, it is usually what is, you see, the amount of voltage carried by the high tension wires, those metallic poles you see within the community, the amount of voltage they carry is about 33 kV. And 33 kV is 33,000 volts. Now, when it comes to the communities, I've forgotten the name of them. Okay, where we have a lot of transformers. If the name comes, I'll tell you. So when it is coming from Akosombo, it is usually this. Then from there, we pick it up, distribute it to the transformers you see within the community. When it comes to the transformers, okay, the transformers are giving 11 kV, which is 11,000. Are the transformers within our community, depending on your need, what factories, houses, schools, whatever, depending on your need, they further step it down. Okay, what comes into our homes is a step down to 240 volts. So because whatever is coming is AC, we can step it down. Now, when it comes to our homes and the gadgets we use, okay, requires higher voltage, then you go and buy a step-up transformer, a step-up transformer, so as to increase the voltage from 240 to whatever you need, a higher amount you need. If your gadget will require a lesser voltage, you buy a step-down transformer, which will still adjust the 240 volts down to whatever you need. That little, okay, please, are you okay?
Yes, sir.
So, because alternating voltage is adjustable, you can either step it up or step it down. It becomes an advantage over DC. As for DC, its magnitude is always fixed. You can't adjust the voltage. So these are some of the advantages alternating current has over direct current.
Sir.
About 4 points. Please, any question?
Yes, sir.
Hello?
Sir.
Gerard, I can hear you. Go
I
ahead.
have a question.
Ask.
Okay, sir. My question is that we said AC doesn't have a fixed current. So please, how are they able to know that the voltage across that AC is 33, whilst the magnitude just keeps changing?
There is, you see, there is a way to streamline the amount. We have what we call AC generator, but we equally have what we also call a DC generator, meaning it is it is DC, it is AC, but we make it look as if it is DC. This time around, we try to filter out the changing direction to behave as if it is moving along one direction. So it is we call it DC generator, though it is an AC, but DC because this time around we've taken out the changing direction and make it flow along one direction. So its graphical representation usually looks as if we have something like this, but it still has that AC nature. So it's because of the use of some devices, which we'll talk about later, commutators, it makes it look as if it is a DC. Okay, so this actually, and this is what comes into our homes. You if we get to electromagnetic induction, you understand what I'm saying better. Okay, so we have DC generators. They are not DC battery. Okay, it is still produced by this rotating, but we make it look like a DC. Are you okay?
Yes, sir.
All right. Please, if you have any question, ask. If you don't have, then let's move on to how AC actually looks like. If you recall, when we were doing simple harmonic motion, we talked about the fact that an example of simple harmonic motion is the motion of electrons in a conductor. So here we were actually referring to alternating currents. We were referring to alternating current, meaning that alternating current is a harmonic function, or is harmonic. Alternating current is harmonic. A harmonic function changes direction and magnitude, okay, or repeated function. So for harmonic functions, this is how we indicated its waveform. Anything harmonic looks like, we say it's sinusoidal. Because AC is harmonic, this is how we represent alternating current. So pictorially or graphically, alternating current is drawn like this. The displacement equation of a harmonic function is given by y is equal to a sine omega t. Okay, so here A represents the amplitude, and the amplitude is the maximum displacement. So from here, the equilibrium position to this point is the amplitude. From here to this point will also give us minus A. Y is the displacement within at any time t. Because AC is also a harmonic function, I said its graphical representation is this. Mathematically or in equation, how do we represent alternating current? It is represented as the displacement equation of a body executing SHM. So I, whether capital I or small I, is equal to IM sine omega t. So this is alternating current or mathematical equation of alternating current. Let me put it as mathematical equation of AC, where we call I, look at this. We said Y is the displacement at any time t. So instantaneous displacement. We call this I as instantaneous current, meaning current within a given time t. Over here, what is A? A is the maximum displacement, which is measured from X to crest.
Mr.
So, hello.
Teacher, please, can you slow down and like explain it again?
Okay. So, mathematically, graphically, okay, or AC is represented as this, a sinusoidal curve, because it's a displacement or it's a harmonic function. Now, mathematically, this is graphically. Mathematically, okay, how do we represent this equation? For harmonics, I said that this equation is mathematically expressed as y is equal to a sine omega t. And we call this as the displacement equation of a body executing simple harmonic motion. Where this y we say is the displacement. Okay. A is the amplitude. The amplitude is the maximum displacement. Omega is that constant or uniform angular velocity. T is any time t. So any harmonic function, any function that changes with time is represented as this. And so mathematically, AC is also represented as this, where we have I, whether small I or big I, is equal to Im sine omega t. Now let's define our letters. This I is known as instantaneous current, meaning if you know Im, omega, and t, you can determine the current at any time t. So I is known as instantaneous current. Please, does it make sense to you?
Yes, sir.
Does it make sense?
Yes.
Then
Yes.
A in SHM, A is known as the what? A is known as
It is the amplitude.
the amplitude. So over here, this looks like the amplitude, but we call this Im maximum current. The amplitude is the maximum displacement. So this is also known as the maximum current or maximum or peak current. So either we call it as the maximum or peak current. So usually the maximum quantity is represented by either Im or IP or I naught. These are the representations you see in the books for maximum current. As for omega, it's because it's a simple and harmonic function. Omega must be fixed. and T is at any time T. Please, are we okay? Are we okay? Ileana and Po, are you okay? Hello. Are you fine?
Yes, sir.
Yes, sir.
AC. You see, whenever there is an EMF induced in a circuit, the EMF drives charges to flow within a conductor. So whenever there is EMF, there will automatically be current because the EMF is the driving force of the charges. So when there is EMF, there will be current. So just as we talk about alternating current, we also talk about alternating voltage. There must be a voltage, which is the EMF, to drive the charges to create current. So we also have alternating voltage. Alternating voltage. So alternating voltage is also simple harmonic. It follows how current is. So we also have, for alternating voltages, we also have V is equal to Vm sine omega t, where V is known as instantaneous voltage Vm is the maximum voltage or peak voltage. And don't forget, from Ohm's law, we said V is directly proportional to I. The potential difference or the voltage drop or EMF is directly proportional to current. So when there's voltage, there will be current. And they are directly proportional, meaning as one increases, the other one also increases. So for alternating systems, we talk about alternating current and alternating voltage. Andrea, are you okay?
Yes, please.
All right. So alternating voltage is also represented as, it's also a harmonic function. If you are representing alternating voltage, this is how the same sign function, where from this part to this part is the maximum voltage, Vm, and then minus Vm. Minus Vm. All right. Now, we also could talk about instantaneous power. Instantaneous power. And that is because power, we know power to be equal to voltage times current. When we multiply instantaneous voltage by instantaneous current, we have instantaneous power, PI. And so VI is Vm sine omega t times instantaneous current Im sine omega t. So P instantaneous is given by Vm times Im sine squared omega t. Vm times Im gives us peak power sine squared omega t for instantaneous power. So instantaneous power is given by the peak or maximum power times sine squared omega t. Please, are we okay? Now, a graphical representation of instantaneous power is given as this. We have the peak or maximum power, PM. So this is equal to, it's a sine function, meaning it will start from the origin. So against time or angle, this is how instantaneous power is represented. The reason why, though it's a harmonic changing function, but there's no, it only flows in one direction, is that the sign is a square. So the sine function is always a square. So even if it's a negative, it will turn to a positive. Okay, so it is along one direction. So this is the graphical representation of PI, where this is the peak or maximum power, and this is the sine function, because it's a square. Even if the time or the angle is a negative, it will be squared to be a positive. So this is instantaneous power. Now let's understand one other quantity, which we will call as root mean square current and voltage. So here we are talking about IRMS and VRMS. Root mean square current and voltage. When we talk about the root mean square current and voltage, please, we are referring to the effective current, that is the effective current or the effective voltage. So please take note that the RMS value of either current or voltage is the effective current or voltage. So IRMS or VRMS is the effective current or voltage. So by RMS value, we are referring to the effective current or voltage, and it is also the current and voltage from the source. So it is also the current and voltage from the source or mains, from the source or main. So in questions, if you are given the source or the main current and voltage, please do not forget that that is the RMS current or voltage. Okay. RMS current or voltage is the effective current or voltage, and it is also the source current or voltage. Now let's understand what we mean by root mean square current and voltage. The root mean square value, please, are you done writing what is here, what is down here?
Yes.
I'm adjusting the screen.
No, please.
Okay. There we are. So when we talk about RMS value of current and voltage, what are we talking about? As I said, it is the effective value of current or voltage, or the current and voltage from the mains. But how do we practically determine RMS value? RMS voltage or current is a comparative thing. We are always comparing. Can I adjust the screen?
Yes, sir.
We are always comparing AC to DC. We are always comparing AC to DC. That the effective current, the equivalent direct current, okay, which will do the same work under the same condition as alternating current. So we are comparing, we have DC and AC, okay? So we are comparing an equivalent direct current which will do the same work as its equivalent alternating current under the same condition is what we refer to as RMS value of current and voltage. So here, what we do is that we pass a certain value of AC through a resistor, R, and do the same thing for DC through the same value of resistor, the same magnitude of resistor, or through the same resistor R, and compare the heating effects both will produce. Okay, so we define RMS current, IRMS. This is the definition. The equivalent direct current that produces the same heating effect, as the alternating current under same conditions. So root mean square current is that equivalent direct current that produces the same heating effect. Let me modify it a little bit. That produces the same heating effect when passed through a resistor R under the same conditions. So we give the alternating current and then the direct current the same conditions, and then pass both of them through a resistor. And when current passes through a resistor, in fact, they will produce heat. So the heating effect produced when DC and AC are passed through a resistor R under the same condition. This equivalent DC is what we refer to as root mean square current, IRMS. So DC, heat energy will be generated, and heat is given by I squared RT energy. So I squared RT. So IDC squared times the resistance of the resistor times the time taken to pass through the conductor. Under the same condition, IRMS, in fact, IRMS over one cycle is given by I peak, the peak current divided by 2. Okay, if you pass alternating current through a resistor, okay, and over one cycle, the average current is given by the peak IM squared over 2. I'm just giving you this. You are not proving this. We can prove it, but what you need is the formula. So if you want to determine the average current over one cycle, and one cycle is from 0 to 360, so you integrate mathematically, you integrate the instantaneous current IM sine omega t from 0 to 360. 360 is 2 pi. And when you do this, this is equal to IM squared over 2. Okay, so the proof of this or the integration of this would give you this, but I don't want us to go through. So the average current over one cycle is equal to this. So in passing this through, the average current squared times the resistance times T. But we've just seen that the average current I average is given by IM over 2. So I maximum over 2 squared. This squared times R times T would give you the heating effect produced by the alternating current. So I DC squared RT. Now, since it's the same resistance, R and R cancels out, we are passing both DC and AC over under the same condition. So we give them the same time. So T and T cancels out. Therefore, we have IDC squared equal to IM squared over 4.
Four.
Okay. Now I'm coming. This is for I average is this. All right, I'm coming. So IDC is equal to the square root of IM squared over 4. This is equal to I maximum over 2. But it should be root 2. It should be root 2, meaning I've mixed out this. I've mixed out this. It should be I maximum over root of 2. Over root of 2. Okay, okay. Yes, the formula is IRMS is equal to IM over root 2. So what I'm envisaging is this. This affects, the square only affects, yes, the square only affects, this I'm coming. The average value will be this. I think I maximum squared over 2. Yes, yes. The average value over one cycle is I peak squared over 2. It isn't affecting all of them. So that if we multiply through the average current, okay, by this, we have IM squared over 2 times RT. Then R and R cancels out, okay? So that when you take the square root at both sides, you have root of IM squared over 2. Then we can have I peak, the square would vanish over root of 2. So this formula is this. The average value is equal to IM squared over 2. Not the 2 doesn't, the power 2 doesn't affect all of them. So by the definition, we define IRMS as the equivalent DC, direct current, that produces the same heating effect when passed through a resistor R under the same condition. So this equivalent DC is what we call as IRMS. IRMS, which is equal to the peak current IM over square root of 2, or 1 over root 2 is 0.7071 IM. 1 over root 2 is equal to this. So either you express it as this, or this is equal to this. That's the expression for the root mean square current, which is also the effective current, and then the current from the mains. We are always expressing current in RMS value. We don't express it in root mean square. Okay, but this is the equation connecting the RMS value and its peak or maximum current to switch from one to the other. Because V is directly proportional to I, if we have I RMS value, we equally would have V RMS value. And it's the same relation. How we derived it is the same thing. So V RMS is also equal to the peak or maximum voltage divided by root of 2, or 0.7071 times the peak voltage. A must a mass known equation, which we will use so much in under AC theory. Please, any question? If you have any question, quickly ask before we continue. Please, this definition very, very important. What is root mean square current? Or what is the root mean square voltage? So take note of this definition. The equivalent DC, which produces the same heating effect as the AC when passed through a resistor, are under the same condition. So if root mean square current, IRMS, is, let's say, 5 ampere, what it simply means is that this is when you given under the same condition, that equivalent AC, DC, under the same condition, the equivalent DC, which will produce the same heating effect as the AC when passed through a resistor, is 5 ampere. If IRMS current is 5 ampere, what does it mean? It means that that equivalent direct current, which will do the same work or produce the same heating effect as the AC under the same condition, is 5 ampere. This is what it means. Under AC, can I clean the board?
Please, can you adjust the board?
Where, down or up?
He's down. Please, I'm done.
Okay. So, Deborah, Araquia,
Mr. D.
explain to me what this means. IRMS current is 15 ampere. What does it mean? Deborah.
Mr. D.
Mm-hmm.
The R I that when you compare like DC will produce on the heating.
The line is even breaking. Okay. Safo. Safo. Safo.
Yes, sir.
IRMS current is 15 ampere. What does it mean? Hey. Obiahedi. Okay. Andre.
Yeah.
What does it mean? IRMS value of current is 15 ampere. What does it mean? How did I okay, Gerard, what will you say?
Okay, so what it means is that the amount of DC current that will produce the same heating effect
The amount of DC. Don't say
yes,
DC current.
DC, sorry, that will produce the same heating effect. That will produce the same heating effect as the AC going through that conductor is 15 amperes.
Going through a resistor R.
A resistor, sorry.
Okay. So what is the definition of RMS? The equivalent, Gerard, don't say the amount. The equivalent DC that will produce the same heating effect. So please listen, all of you. The equivalent direct current that will produce the same heating effect as the alternating current going through a resistor R under the same condition as 15 ampere. That is what it means. Okay. IRMS is the equivalent direct current that produces the same heating effect as the alternating current through a resistor, okay, under the same condition. So if you give me IRMS value, it means that equivalent DC, which will produce the same heating effect as the AC through a resistor R under the same condition as that value given to me, period. So Deborah and Co, this is how you explain it, okay? All right.
Yes, please.
Okay, sir.
Let me clean the board so we could continue. Now we look at when AC is passed through components, some components, such as a resistor, a capacitor, an inductor, what happens? When you have circuit components, such as a resistor, capacitor, and then an inductor, and you pass alternating current through them, what happens? So over here, we'll be looking at the effect of AC on some circuit components such as a resistor R, an inductor L, and a capacitor C. Within a circuit, these circuit components are represented by the following symbol. So within a circuit, the circuit components are represented by a resistor is represented as this. So we have for a resistor, it isn't new to you because we've done this DC with R on top, or it is also represented as this with R on top. So this is how in a circuit a resistor is represented by a capacitor. Is also represented as equal parallel lines. So in a circuit, this is how a capacitor is also denoted or represented by. Then an inductor. An inductor is similar to, I think a capacitor has another old representation. Or either this, okay, for now, if I recall, I'll tell you because we'll just be going into it. So let me, once I have the known one in mind, if I recall the other one, I'll give it to you. An inductor is also similar to this. It's similar to this one. But this is how an inductor is a coil. So L on top indicates that it is an inductor. Please, it is similar to this, but they are not the same. This is zigzag and this is a coil. Okay. So we'll be looking at the effect of alternating current on this circuit components. All right. Now let's begin with a resistor. So effects of AC on a resistor. So we call this as resistive components. We'll call this as resistive component. So if I have an AC, alternating current, and alternating current in a circuit is represented by this. Okay. Unlike a DC or yes, a DC source where we indicate positive and negative. This time here we don't do any indication. When this is connected to a resistor, what happens? R. Of course, current I flows. Now, from Ohm's law, we saw that whenever you connect a battery to a resistor, and then you connect a voltmeter across the resistor, the voltage across the resistor is directly proportional to the current flow, meaning an increase in the voltage drop is directly proportional to the current flow within the circuit. As the voltage increases, current would also increase. And now, pure resistive circuit, which is this. This is also a pure resistive circuit. we have the same relationship. Ohm's law is also obeyed. Whenever you pass current, alternating current across a resistor and you connect a voltmeter to determine the voltage drop, you still have the voltage being directly proportional to the current flow, RMS value of the current. Okay, so that linear relationship is still there. Okay, so we say that for the conclusion is that for a purely resistive circuit, resistive circuit, the voltage drop or the potential difference is linearly to the current flow or the flow of current. I. If the voltage is linearly to the current flow, it implies that both quantities are along the same direction. So both current and voltage are along the same direction. If they are along the same direction, then we can also say that I and V are in phase. Okay. Then,
Yeah.
hello.
I can't see.
Oh, let me read it for you to write.
Okay.
So I said for a purely resistive circuit. And what is a purely resistive circuit? It's a circuit with an alternating current source connected to a resistor. So this arrangement is what we call as a purely resistive circuit. This connection. So for a purely resistive circuit, we are looking at an AC, an alternating current source connected to a resistor. And if you connect a voltmeter across the resistor, I'm coming, Andre, I'm coming. You will get Ohm's law is obeyed. Ohm's law is obeyed. The voltage is directly proportional to the alternating current. V is directly proportional to I. If V is directly proportional to I, then the conclusion is that for a purely resistive circuit, the voltage drop or the potential difference is linearly to the current flow. Linearly to the current flow. If it is linearly to the current flow, then we can deduce that both current and voltage or potential difference are along the same direction, or both current and voltage drop are in phase. Andrew, are you there? Andrew, are you there? Andrew is gone.
Yeah, I'm here.
Now, Gerard, when two quantities are in phase, what does it mean? When two quantities are said to be in phase, what does it mean?
It means that
Gerard, I'm listening.
okay. So what I'm saying is that when they say they are in phase, that means they all reach their maximum value at the same time, get to zero at the same time, and then come to negative at the same time.
Okay.
Have their minimum at the same time.
So, when two quantities are said to be in phase, they occur at the same angle, okay, and they are all along the same direction. Okay, so it means both voltage and current are along the same direction, meaning they are in phase. If we draw the phasor diagram, okay, phasor diagram, the phasor diagram for current and voltage. For phasor diagram, this word comes from phase and then the word vector. So we pick F-A, F-H-A-S and add O-R to make it phasor. No, we pick this F-H-A-S and then we just add O-R to make it phasor. So phasor diagram is the angle, okay, or the fact that two quantities are along the same direction, okay, they achieve their maximum minimum together at the same direction. So a phasor diagram or a vector representation of this quantities in phase. So let me write the explanation. Phasor is a vector representation of quantities in phase. That is what we mean by phasor diagram. A vector representation of quantities in phase. And here we are talking about the quantity, voltage, and then current. For purely resistive circuits, the voltage is in phase with, so you draw the direction of the current okay, please here we represent it. We do the representation on the XY axis. Okay. The current is positive, so we place it along the positive X. They are at the same angle. Then the voltage is also along the same direction. So the same direction, the voltage V is also along the same direction. So this arrow for the current, and then this arrow for the voltage, the same direction, meaning the two quantities are in phase. So usually when you are drawing this, fine, you don't, this is for explanation because we'll be looking at other quantities that are also either in phase or out of phase. But when you are drawing a phasor diagram for a purely resistive circuit, you just draw this, a horizontal line, indicate the first as I, and then indicate the second one as voltage, to mean that they are in phase. Please, is that okay?
Yes, sir.
All right. So that is it for purely resistive circuit. And don't forget that this I and then the V are RMS values, effective values of current and voltage. So if I don't indicate it, then it means we are looking at the effective value of current and then the voltage. We use the root mean square quantities. All right. Then let's look at alternating current through the other components, capacitor and then the inductor. Let's look at it for a capacitor. Please, what is a capacitor? What is a capacitor?
This a capacitor is an electronic device that stores charges.
Okay, so Nidino no Honam say a capacitor has the capacity to store charges. Hello. Hello.
Please, after the flow of current, please, what's next? The light is reflecting at that side.
I said both current and voltage are along the same direction. Both current and voltage are along the same direction.
Mr. Dear,
Yes.
please can you say that like to say let's say two quantities are in phase, can you say they move in the same direction?
Yes. That's what I said. They're along the same direction. That is why look at the phasor representation or the phasor diagram. This is the direction of current. This is also the direction of voltage. They move along the same direction.
Yes.
Okay. So when you pass AC through a capacitor, and as you said, it's an electronic device that stores charges. We call this circuit as a purely capacitive circuit. So in a purely capacitive circuit, we have a capacitor connected to an alternating current source. Now, when you connect a capacitor to DC, what happens? This is a capacitor connected to a direct current source. So we saw that.
Mr. Dear,
Hello.
please are you saying what happens when you connect a capacitor to a direct current?
A direct current source. A battery.
Mr. Dear, please can you say that like the charges cannot a current won't pass through because when it reaches the capacitor, it will store the charge.
Oh yes. You see, I'm coming to talk about it. So you see, a capacitor when you connect a DC source or voltage V or EMF E, and then you connect a voltmeter across the capacitor, you realize that the voltage drop V across the capacitor will be directly proportional to the charge stored on the capacitor plates. So as the charge stored on the plate increases, then the voltage drop across the capacitor also increases. Now, at the point where the voltage drop across the capacitor is equal to the EMF of the battery, then we say the battery at the capacitor is fully charged. Capacitor is said to be fully charged. So, in short, capacitor is said to be fully charged when the voltage drop across the capacitor is equal to the EMF of the battery. And because the voltage drop V or delta V is directly proportional to Q, okay, so it's like V measures the amount of charge stored on the capacitor plates. Because V is equal to a constant of proportionality K times Q. Now, if you make K the subject, okay, you have V on Q. I'm coming. Let me see. Q is directly proportional to V. Yes, yes. It's rather Q being directly proportional to the voltage of delta V. So the greater the Q, the greater will be the voltage drop. Please, this relationship is that if you mix, okay, how they relate, it will change the whole thing. So Q is rather directly proportional to the voltage drop, change in the voltage drop V across the capacitor. Now, if we introduce a constant of proportionality, we have K on delta V. If we make K the subject, we have Q on delta V. And Q on V, charge over voltage, is what we call as the capacitance of the capacitor. So the constant of proportionality here is what we call as C, which is the C is known as the capacitance of the capacitor. And the capacitance of the capacitor is a measure of how that is a measure of the ability of the capacitor to store charges. The capacitance of the capacitor C is the measure of the ability of the capacitor to store charges. Please, you have to put that down. That's why I'm not giving that to you. The capacitance of the capacitor is the measure of the ability of the capacitor to store charges. Are we okay? Hello, are we okay?
Yes, sir.
So, for a capacitor connected to a battery, the charge Q stored on a capacitor plate is directly proportional to the change in potential across the capacitor. So if the change in potential, delta V, is equal to the EMF, then the capacitor is said to be fully charged. Then you have to disconnect it. It's like you are done charging the capacitor. So you'll be done charging if the voltage drop across it, measured by a voltmeter, is equal to the EMF of the battery. Now, so to charge a capacitor is charged using a DC source. You cannot use an AC source to charge a capacitor. You cannot use an alternating current source to charge a capacitor. You can only do so using a direct current source. This is the reason. When you use DC, because AC flows in two directions. One directional flow of the current stores the charges or charges the capacitor. The other directional flow discharges the capacitor. So in effect, no work will be done. So if you connect an AC for a purely capacitive circuit, it will be cos 90 job. So because AC flows in two directions, positive and then negative, it means that during one cycle, the capacitor will be charging. So you realize that, let me draw a quick circuit. If you connect a voltmeter across the capacitor, V, the observation is that during one cycle flow of the current, this is flowing in this direction. The current flows in this direction. The capacitor gets charged. So you realize that the voltage drop or the charge stored on the capacitor plates Q is directly proportional to delta V, fully charged along one direction. In the other directional flow, when the current flows in the opposite direction, the capacitor is discharged, comes back to zero. So no, at the end of it, the work done or the charge is zero. So no work will be done when capacitor is connected to an alternating current source, because one directional flow of the capacitor charges it, the other directional flow discharges it. So no work is done when AC source is connected to a capacitor. This is because one directional flow of the current charges the capacitor, and the other directional flow discharges the capacitor. So in effect, no work will be done. So this is one of the applications where the use of AC becomes a nuisance or a problem. Okay, so one application where the use of alternating current, which is very, very important, becomes a problem. Becomes a problem is during charging a capacitor, because in charging a capacitor, the capacitor is charged in one direction and then discharges in the other direction. Another application where the use of AC is not needed, apart from charging a capacitor, is separation of ions, electrolysis. So electrolysis also would require a DC source and not AC. Okay, so two applications where the use of alternating current source AC becomes a nuisance or an unwanted entity. One, in charging a capacitor, and then separation of ions, which is electrolysis. These applications would require the use of a DC and not AC. Please, are we okay?
Yes, sir.
Yes,
Hello.
sir.
Okay. So let's look at the phasor diagram. Okay. The phasor diagram of a purely capacitive circuit is that over here, when you connect it to AC, the current flow, okay, quickly leads the voltage by an angle of 90. We can show that by mathematical expression, but you don't need that. So I'm just giving that to you. When you connect AC to a capacitor, the current flow would actually lead the voltage drop across the capacitor. So this is the voltage drop across the capacitor, and we could determine that using a voltmeter. So we've connected. So unlike in purely resistive circuit, where the voltage drop across the resistor is directly proportional to the current flow, over here, the voltage drop across the capacitor, delta V, okay, yes, lags behind the current flow. The current flow I. Or instead of saying delta V, this is delta V, not the source EM. I mean the voltage drop across the capacitor. Or the current I leads the voltage drop, delta V, by an angle of 90 degrees or pi on 2 radian. So for a purely capacitive circuit, current leads the voltage drop, okay, by an angle of 90 degrees or pi on 2 radian. For purely resistive, they are all in phase along one direction. So the phasor diagram for a purely capacitive circuit. Phasor diagram for a purely capacitive circuit. Is equal to, or is run by, you see, we are always representing the current direction along the x positive. So current, as we did for purely resistive, I is always here. Over here, the current leads the voltage by 90. So if I identify the current, I need to measure an angle of 90 degrees up. Oh, hold on. Okay. So this is leading, and this is behind it by 90. By 90 degrees. And I have the voltage drop lagging behind the current by that angular margin. So this is VC, or what we have indicated here as delta V. VC to indicate voltage across the capacitor. This lags behind the current by 90 degrees. So this is the phasor diagram for a purely capacitive circuit. Please, if you have any question, quickly ask before we continue. So this is behind. DC is behind current by this margin. Okay, so voltage lags behind the current, or current leads the voltage. Now let's look at purely inactive circuits. What is an inductor? An inductor behaves as, please, are you done drawing? Are you done?
No, please read the top parts.
So when you finish, let me know.
I'm done.
Okay. What is an inductor? An inductor behaves as a resistor. But the difference is that an inductor opposes alternating current. As for a resistor, it opposes both DC and AC. But for an inductor, it opposes only alternating current. If you are a current and you are not changing direction and magnitude, an inductor has no problem with you. But the moment the current changes direction and magnitude, an inductor has a problem with you. So in a circuit, if you connect a resistor and an inductor, this is how the two behaves. Deborah, Erequia, Andre. Who else? Andre, Erequia, Irene. Eliana is gone. Yo. Amunko. So if you have a circuit connected, this is a DC. Maybe there is a resistor within the circuit. Even if there's no resistor, the wires offer some resistance. So there's a bulb. The wires are offering a certain level of resistance. Within the same circuit, if we connect an inductor, let me incorporate a resistor, an external resistor, meaning the resistance will go up because resistance by the wires and resistance by this fixed resistor R. Within the same circuit, we have an inductor connected to a bulb. This would offer a certain level of opposition to the flow of current, but it will never change the brightness of the bulb. Okay, it will resist it, and by resisting the current, it will drop the current flow. But whatever is turned out will be constant, wouldn't change again. Is that okay? And whatever will be turned out is what will brighten the bulb. And the bulb's brightness stays constant, will not change. When you connect an inductor and the current is a DC source, or the source is DC, nothing will happen. It will behave like the resistor. The bulb's brightness will be fixed, no change in brightness. But the moment the source is a DC, sorry, AC, then something would happen. When the source is AC, an inductor always opposes a changing current. A current changing by direction and magnitude. So this is where it has a problem with you. What will happen to the bulb is that the bulb will delay in brightening. It will start smaller and then the brightness will be increasing. So its brightness will be delayed. So when the source is an AC, the inductor delays the glowing or brightness of the bulb. Meanwhile, the same component, if the source is DC, there will be nothing. It will just behave as a resistor. But the moment the source is an AC, the inductor delays the glowing of the bulb from little to maximum. It will delay it. So an inductor, okay, opposes changing current. Please, are you okay? Are we okay?
Yes, sir.
That's the concept. An inductor opposes changing current. Now, so in a circuit, whenever you want the flow of current within a component to be delayed in order to protect maybe some component, a delicate component, you see an inductor there. Okay, so maybe the component are such that when the current flows through its maximally, it can damage it, such as transistors. Okay, transistors. Then we incorporate an inductor so that it delays the flow of current from minimum to maximum. That is why in most electronic appliances, you see a coil, an inductor within, and its purpose is to delay alternating current so as to maybe protect delicate. So if you see the fluorescent tube, there is an inductor within. Okay, that's why when you on a fluorescent tube, it takes time to brighten. Then it comes on quickly. Okay, so it's the inductor which controls the flow of current from minimum to maximum. So it delays, the inductor delays the current, okay, so as to build up gradually. So for purely inactive circuits, the current is behind the voltage. So if you on a fluorescent tube or fan, you hear a humming sound first before the current glows gradually to maximum. All components that behave as such has an inductor within. Please, any question? Okay, Gerard.
Peter, please, you blocked my view.
Okay. All right. I think we are ending. So I think we'll end here. But if finish writing, if you have any question, ask. If you don't have any question,
Yes,
then
I'm done.
okay, then we end here. Okay. I'll notify you as we went to continue tomorrow and all that. Please, good night to all of you. Okay. Hey, I said good night to all of you. Oh, come on. Okay, bye-bye.